Hi, in video number 22 on probability for actuarial exam P, we're going to be considering what you might call a generalized expectation, a generalized expected value, or the expected value of a transform random variable to solve a practical problem about payment of an insurance company towards somebody being in the hospital. The numbers involved are not really practical, but the idea is pretty practical. So here's how I'm describing the question. Determine the expected mean payment, an amount of money, for hospitalization of a person in a hospital based on a PMF, probability mass function, of not the payment amount, but instead the number of days in the hospital. And then I'm going to extend the problem that you find on the sample exam online question 44. We're going to also find the PMF, probability mass function, of the payment amount itself. That payment amount is a transform random variable in terms of the number of days. Okay, so it's kind of abstract concepts here. Let's get into the problem and try to make it more concrete. So again, question 44. An insurance policy pays $100 per day for up to 3 days and $50 per day for each day of hospitalization thereafter. And if you look at this formula here, you see that the number of days in the hospital, according to this model, which is a simplification of an oversimplification of reality, you might say, the number of days in the hospital can either be 1, 2, 3, or 4, or 5, these values of k here. Yeah, the number of days of hospitalization, x, is a discrete random variable with probability mass function that you see here. Let me go ahead and give some special notation for this. Let's call it little p sub x to emphasize that it's going to be the probability mass function for x. We're going to have a second random variable y in this problem. Oftentimes we say the variable for this is little x, but here because we see a little k, I'm going to put a little k in here. I could use a little x, it doesn't matter. That's the probability that the random variable x equals the value of k, and it's given by this formula. If k is 1, 2, 3, 4, or 5, use this. The value of this is 0 otherwise. Like if k was 6 or 7, there's no chance that a person stays for 6 or 7 or more days. And you also can't stay a fractional number of days, 1.2 days, even though in reality you could leave in a fraction of a day. We are considering even partial days to be full days here. Let's go ahead and, before looking at these questions, write down the values of this function at these values of k. Px of 1, the probability that a person stays 1 day in the hospital. Plug in k equals 1 right there. You get 6 minus 1 over 15 is 5/15, which of course reduces to 1/3, but I'm going to keep it as 5/15. Px of 2 is going to be 6 minus 2 over 15, which is 4/15. Px of 3 is going to be 6 minus 3 over 15, which is 3/15, which reduces to 1/5, 0.2. But I'll leave it as is. Px of 4, the probability that a randomly chosen person stays 4 days, is 6 minus 4 over 15 is 2/15. And finally, Px of 5 is 6 minus 5 over 15 is 1/15. And take the time to double check that if you add up all those numbers, you do indeed get 1, as you should with a discrete probability model, a discrete random variable. Okay, part A is to determine the expected or mean payment, not number of days, but payment for hospitalization under this policy. That's what the online sample exam problems 44 here ask you to do, but I added an extra part, part B. I also want to determine, for the purposes of understanding stuff, the PMF of the payment random variable. Not X, but Y, say the amount that is paid by the insurance company. Okay, so again, a very practical question, a fairly simple model here. You know, you might say it's somewhat realistic. Of course, people can stay longer than 5 days, but maybe in a certain hospital that's so rare that you consider the chances of that effectively 0. These payment amounts are pretty small. They'd be typically bigger than that, but let's just go ahead and use these numbers here that we have. All right, so how do you do part A? Well, we have to define a new random variable first. Call it capital Y. I want to find the mean payment, not the mean number of days. This is the payment amount random variable. It's a discrete random variable that can equal what? Think about it here. Go back up here. It would equal 100 if the person stays 1 day, 200 if they stay 2 days, 300 if they stay 3 days, 350 if they stay 4 days, and 400 if they stay 5 days, right? Because it goes up by 100 per day for up to 3 days and then up by 50 per day thereafter. Okay, this is really a function of the number of days. I'm going to call it g of x. So g is my function name. In probability, in this kind of situation, it's common to call this a transformation. Transformation. But that really is just the same name. It just means function. It's just another word for function. In some contexts, like linear algebra, for example, a transformation is often thought of geometrically. In this situation, it's not really so geometric, but we go ahead and use the word transformation anyway because you'll see it in books that way. This is a transformation. G is the name of the transformation, and it's got a formula. It's really a piecewise formula depending on whether x is 1, 2, or 3 versus whether x is 4 or 5. If x is 1, 2, or 3, think about it. Its formula is going to be 100 times x, right? If x is 1, you get 100. If x is 2, you get 200. If x is 3, you get 300. That's if x is 1, 2, or 3. It's a little trickier in the case where x is 4 or 5. Maybe you want to pause the video and see if you can figure it out on your own. You're back now. It goes up by 50 per day, but of course for the first 3 days there's the base amount of 300. Then you add 50 for each extra beyond that, and if you think about it, here's a nice way to get that. 50 times, in parentheses, x minus 3 plus 300. If x is 4, for example, this will be 50 times 1 plus 300 is 350. If x is 5, you get 50 times 2 plus 300 is 400. This does simplify, of course. If you distribute the 50 through, you get 50x minus 150 and then a plus 300. This is the same as 50x plus 150 ultimately, but it's a little easier to think of it this way first. All right, well, what's the mean of this variable then? What is the expected value of y, which would be the mean payment? It should be in the hundreds, right? It should be between 100 and 400 somewhere. Sometimes this would be written in terms of the transformation. It's the expected value of g of x. And to solve the problem here as quick as possible, I'm just going to write down the formula you would find in books for this generalized expected value. But again, I do want to talk about why it makes sense. I'm going to talk about why it makes sense in two ways. Well, and one of the ways is going to involve doing part B. And the other way is going to involve going to Mathematica and doing a simulation like I did in the video number 21. We looked at a simulation. All right, so the formula that you'll find in textbooks in this kind of situation is you want to add up the values of g times the corresponding PMF values. I purposely left those parentheses blank at first because I really want to emphasize you could use either little x or little k inside here and here. Just to be consistent with this, up here I'll use a little k, but it would not be wrong to use a little x as the values of capital X in this case. Little k goes from 1 to 5. Okay, so again, this is going to be what you'll find in books how to do this. And how does the calculation go? Think about it here. The values of g are 100, 200, 300, then 350, then 400. The corresponding probabilities are these numbers. So g of 1 is 100 times p of 1 is 5/15. G of 2 is 200. P of 2 is 4/15. There's a 4 there. G of 3 is 300. Probability that they stay 3 days is 3/15. G of 4 is 350. Careful not to make a mistake. I almost wrote 400 times 2/15, and then G of 5 is 400 times 1/15. So this becomes 500 plus 800 plus 900 plus 700 plus 400 over 15, which is 3,300 over 15. And if you use your calculator, that'll come out to 220. And that is the answer. That's answer C on the sample exam that you can find online, and that is correct. It's between 100 and 400 as we expected. Pun intended there. But now we want to understand this formula again. Why does this make sense? Why can we use the PMF for x to find a mean for y. Maybe it would help to find the PMF for y and see that we would get the same answer. Okay, that's a little tricky here. One thing you could do, I mean, this the simplest thing to do, but it doesn't generalize quite as easily. So I'm going to go do this in two ways. One thing you could do is you could just write down the formula for the PMF P sub capital Y of little y of y, capital Y, the payment amount, as a piecewise formula. The probabilities for this are going to be the same as these probabilities. We'll get the same numbers here, same 5 possibilities, but the values of little y, of capital Y itself, are not 1, 2, 3, 4, and 5. They are 100, 200, 300, 350, and 400. So at the most basic level, we could just do something like this. Okay, but I'm going to show you a fancier way to do it here in a minute that also generalizes more easily. So these are the different probabilities. This is if little y equals 100. This is if little y is 200. This is if little y is 300. This is if little y is 350. And this is if little y is 400. Okay, so those are the values. That's one way to describe the PMF. And if you do it this way, you do see pretty much immediately why this is going to give you the right answer, because we do have the values of capital Y that it can take and these corresponding probabilities. It is an ordinary summation that would give you a mean for Y when you think about it that way. Okay, but let's get a little fancier now, again, for the purposes of generalization. What we can do instead to generalize is we can also use this transformation. We can find its inverse transformation. That's going to be actually helpful here. Let's do that a little further down. So just to remind you, I did essentially explain why this formula makes sense based on this, but I'm trying to generalize this here in a way that'll be helpful in the future. Find an inverse function for this. Now, is this function invertible? We are thinking about it as just being defined in a finite domain, by the way. For these 5 values of x, 1, 2, 3, 4, and 5, we get 5 distinct values of y. 100, 200, 300, 350, and 400. Defined in a finite set, definitely that's an invertible function. And I can find its inverse. X equals g inverse of y. And it would be piecewise. In the case where x is 1, 2, or 3, we use this formula, 100 equals 1, y equals 100x, and solve for x. Divide by 100. You get y over 100. In the case where capital Y is 100, 200, or 300, then you'll get a value of x that will be 1, 2, or 3 in those cases. In the case where x is 4 or 5, and y is 350 or 400, we need a different formula. We need to look at y equaling 50x plus 150 and solve that for x by subtracting 150 and then dividing both sides by 50. You would get y minus 150 over 50 if y is 350 or 400. Okay? Double check that that works. If y is 350, you get 350 minus 150 is 200. 200 divided by 50 is 4. Get that value of x. And if y is 400, we get 400 minus 150 is 250, divided by 50 is 5. Okay? This is the inverse function. How can this now be used to write an alternative formula for the PMF of y that I'm going to, again, call P sub y of little y? And again, even with discrete PMFs, you typically do want to define them for all real values of the variable here. So I will write it piecewise. Well, think about this here. You want to get these same probabilities that we got up here. The little k's represented the values of x. G inverse of little y, say, if I replace capital Y with little y, would also be values of x. 1, 2, 3, or 4, or 5. So what I need to do is use the same formula up here, except replace k with G inverse of y. Does that make sense? 6 minus G inverse of little y divided by 15. But if, not if little y is these values, but instead if little y is 100, 200, 300, 350, or 400, and 0 otherwise. double check that this works. If you plug in little y equals 100 here, g inverse of 100 is 1. 6 minus 1 divided by 15 is 5/15. Plug in 350, for example. G inverse of 350 we saw was 4. 6 minus 4 over 15 is 2/15. It does work. This is a formulaic way of writing the PMF of y, and so it's going to be a more general approach that works in harder problems than just doing something like this. Okay, and once again, the values can be used then to find this exact same formula for the expected values we found before. Now let's go to Mathematica and confirm that this all makes sense with simulation, like I showed you in video number 21. Okay, so here is the PMF of x. I'm not doing it as a piecewise function. That's fine. I'll just keep in mind that k is 1, 2, 3, 4, or 5. I can make a discrete plot of that. Those are the probabilities, the 5/15, the 4/15, the 3/15, the 2/15, and the 1/15. These do all add up to 1. There's a confirmation of that. Here's going to be a summation that gives you the mean of x, which we never found in this problem. I'm going to do it in Mathematica here. We never actually found the mean number of days in the hospital, but just for the sake of interest, what is it? It's got to be between 1 and 5. It's 7/3, which is 2 1/3 days. Here's the g of x function, the transformation. That is a piecewise function. Here's the summation that got us our mean, that got the mean to be 220. This should be 220, and it is. And here's where we can do the simulation. I can define a probability distribution based on this PMF for x, calling it dx, and then I can use something called random variate to generate simulated data. So these are going to be 1,000 numbers that are a bunch of 1s, 2s, 3s, 4s, and 5s. And there should be a lot more 1s, for example, than 5s. Okay, 1 should occur about 1/3 of the time. 5 should only occur about 1/15 of the time. And you can just glance through that and check that. And then we can calculate the mean of it. It should be close to 2 1/3, close to 2.3. Yep, it is. And then we can do something similar for y. Here's the g inverse function. Technically, I'm defining it in such a way that I'm defining it for other values of y here, but don't worry about that. I'm just focused on y being 100, 200, 300, 350, and 400. Here I'm defining the PMF, probability mass function of y. I'm using an OR function in Mathematica and a NOT function to do cases here. I probably didn't have to do that, since I am only going to plug in 100, 200, 300, 350, and 400. Actually, I think I did do that for a reason, because it makes this thing down here work perhaps better. So the sum of these should be 1. That's 1. Yep, it's a PMF. Here's a plot of it. It's not a perfect discrete plot. It doesn't do a perfect job. It makes these not just lines. They look like they have a little bit of width to them. That's a little bit misleading. They shouldn't. Here's the probability distribution, and here I can do the simulation. Bunch of 100s, 200s, 300s, 350s, and 400s. 100 occurs about 1/3 of the time. 400, on the other hand, occurs only about 1/15 of the time. And the mean of these should be close to 220. Okay, 217.85. By the way, when you redo the simulation, I'll put a semicolon here to suppress the output. I do get a different mean when I run the simulation again. Okay, you see that? The mean changed a little bit. Run it again, the mean will change a little bit. But no matter what you do, it's close to 220, and so that's a simulation confirmation that we were doing the right thing. Thanks for watching.